Hey class, what we're going to do now is wrap up chapter 3 with section 3.4. So we're still talking about zeros of polynomial functions. We've been talking about those guys since the beginning of the semester, actually. We just kind of honed in on some skills that help us find zeros in this particular chapter, specifically for polynomial functions. So we're going to take all the techniques, factoring, synthetic division, using our calculator, all the techniques that we've seen before are going to all come together here in this section to wrap up our work with chapter 3 on finding zeros. So we're going to use the fundamental theorem of algebra. That's going to help us determine the number of zeros our polynomial functions will have. We'll look at I'm not sure if we're going to look at the rational zeros test or not, but we'll look at how complex zeros come about, those guys that are imaginary. We'll look at the linear factorization theorem, finding zeros by factoring, which is something we did before, and then we'll look at a real life application that involves a polynomial function. Okay, so we're going to incorporate again several techniques that we have learned here in chapter 3 to continue and finalize our work. So right here I've got a listing. We will do some factoring. We may use the quadratic formula. We'll do some synthetic division, and we'll also use some features on our calculator. So here's some important information when we talk about finding all the zeros. When we talk about all zeros, in this section, we're going to work on finding those that are real and those that are imaginary. Those that have an I, complex numbers. Now, the real zeros are your x-intercepts. So everything, all the zeros that we found up to this point have been real zeros, and the real zeros are our x-intercepts. But it is possible that your function could have imaginary zeros. Obviously, those aren't x-intercepts because you can't graph an imaginary number in a real coordinate system. But we'll want to make a note that, hey, some zeros are imaginary. So here we've got just an integer value, that's a zero, also called a rational number. Here, 1/2 is a rational number, so these two guys are rational zeros, which fall under the real zero category. We may come up with irrational zeros. You've seen those come up before. Irrational zeros involve that square root. Irrational just means that the decimal goes on and on and on forever, and it never stops. It doesn't repeat, it doesn't stop. So we've seen this type of zero, this type of zero, this type of zero, and that type of zero in our previous work. Now we'll come across some complex imaginary zeros, and they may involve the imaginary unit I. With the addition of these imaginary zeros, we will have covered all possible bases for zeros of a polynomial function. So the real zeros are our x-intercept, the non-real x-intercepts, the non-real zeros are those imaginary ones. Now remember, in the past, we always said an nth degree polynomial would have exactly n zeros. Well, it also means it will have exactly n linear factors. So just a couple of notes. That degree n tells me I'll have n zeros when we include imaginary zeros and repeated zeros. Okay, so that degree of n tells me exactly how many zeros I'm going to be looking for. And if you remember, every zero has a factor associated with it. So if I have a polynomial of degree n, it can be expressed precisely using n linear factors. And so this is the linear factorization theorem. And they're saying that some of these zeros can be complex numbers, such as an imaginary number. So if I had a function, let's say that had the zeros of, let's say 1, -2, square root of 3, negative square root of 3, 5i, and a -5i. Let's just say I had a polynomial function and I was given this list of 2, 4, 6 zeros. Then I know that this would be a 6th degree polynomial function, because I have 1, 2, 3, 4, 5, 6 zeros. And anytime you have a zero, you can list that zero as a factor. So this zero of 1 could be written as a factor of x minus 1. This zero of -2 could be written as x plus 2. This zero, x minus the square root of 3. This zero, x plus the square root of 3. And the other two guys, I've run out of room, but he would be written as x minus 5i, and the other one would be written as x plus 5i. How many factors? 1, 2, 3, 4, 5, 6. 6 linear factors. The word linear means they just all have a degree of 1. The degree on each of those factors is 1. That's the linear factorization theorem. Now let me back up a second and say this. Whenever you have an irrational zero, like a square root of 2 or a square root of 13, these will always, always, always occur in a pair. When you have these imaginary, complex imaginary zeros, these will always occur in a pair. They always have to have a matching conjugate. So what does the word conjugate mean? Let's see. I'm just going to, right here. Let's talk about conjugates. Okay, if I had, let's just say x plus 3. His conjugate is x minus 3. We just changed that middle sign. So if I had a -2i, his conjugate would be a positive 2i. Because this could be written as 0 minus 2i or 0 plus 2i. If I had the square root of 13, his conjugate would be a negative square root of 13. This is how conjugates work. If I had a zero of 1 plus the square root of 2, his conjugate would be 1 minus the square root of 2. So when you have zeros that are imaginary or irrational, they must always occur in conjugate pairs. You'll see why that's the case as we go on, but I just want you to keep that in mind right now. Okay, so let's go further. Where does this imaginary number come from? Well, it comes from taking the square root of a negative number. Remember, we've restricted our domains and said we can't take the square root of a negative number because it's not in the real number system. Well, now we're saying we can take the square root of a negative number, and that is in the complex number system. So I comes from the definition of the square root of -1. So if I had the square root of -25 in the real number system, that doesn't exist. But in the complex number system, we would call that 5i. Take the square root of 25, which is 5, and that square root of the negative just comes out as an I. So if I had the square root of -9, that means it would be a complex number of 3i. What if I had the square root of a -64? What's the square root of 64? 8, but because it was negative, I have to put an I on the end. When we write a complex number, there's a standard form where there could be a real part and then plus or minus the imaginary part. So actually, we could write the number 3 as a complex number because we could call it 3 plus 0i. Or I could write the number -7 as a complex number, -7 plus 0i. This is just how the complex number system can be developed. So it's like the complex number system does include these real numbers of like 3 and -7 because I can always add a plus 0i next to anything. If I had this complex number, 5 plus 4i, 5 is the real part, the 4 is the imaginary part. Over here, -7 is the real part, 0i is the imaginary part, and so on. Real, imaginary. For 5 plus 4i, what would this guy's conjugate be? It would be 5 minus 4i. But again, the first part is the real part, the second part is the imaginary part. So there's our definition of what a complex number might look like and how that imaginary portion comes about. Another definition working with this I is I squared is always equal to -1. It's just a definition, and that's what we're going to go with. So, I need to pull that up. All right. So here are some examples. We've got a first-degree polynomial function. It's listed as f of x equal x minus 2, and it has exactly 1 0 of x equal 2. It's a first degree. Okay, we've got a second-degree function, x squared minus 6x plus 9. It's going to have 2 zeros, and if I factor it, I'd see x minus 3 times x minus 3 as its two factors. So it has exactly 2 zeros, 3 and another 3 from the other factor. So when I include the repeated zeros, I will always have the exact number of zeros as the degree of that polynomial function. Here's a third-degree polynomial function. Notice it was factored and x was taken out. And when that x was taken out, we were left with x squared plus 4. And if I take x squared plus 4 and set it to 0, he's going to give me two answers. When I subtract the 4 on the other side, then square root both sides, notice I'm square rooting a -4. And for my work above, square root of a negative number is going to be imaginary. And since I square rooted both sides, I have to get a plus or minus. Aha! That is why imaginary solutions will always come as a conjugate pair, because they come from a quadratic. And when you square root both sides of this quadratic, you get a plus or minus, so plus or minus 2i. So notice it was a third degree polynomial, and it has a 0 of 0 from the first factor, and a positive and a negative 2i, which are conjugates. So I am going to stop this video here and then pick up with the next video on what's going to be our approach to finding all the zeros now, all the real ones and all the imaginary ones.